Fine. You already know DFS topological sort. Now let's learn the second and equally important approach, which is Kahn's algorithm. Many interviewers actually prefer Kahn's algorithm because this is easy cell detection, cycle detection, easy topological ordering, no recursion. What problem does Kahn's algorithm solve? So the problem is the same as topological sort, which is if a directed graph or a tag, and you have to find out the ordering, the correct ordering, where every u to v edge u comes before v in the order. Then that is the problem that we want to solve. Okay. So the entire algorithm is based on what concept, which is in degree. So we track the number of incoming edges. We make a vector which is in degree vector. For example, here 0 goes to 1 and goes to 2, 1 goes to 3, and 2 goes to 3. There is no cycle, but the in degree of 0 is 0. The in degree of 1 is 1. The in degree of 2 is 1. And the in degree of 3 is 2. If a node has in degree 0, then it has no dependencies and we can safely place it first. This is the entire intuition behind Kahn's algorithm. Once you place an in degree, you subtract the in degree of all the neighboring elements to it. Okay. Reduce the in degree of the neighbors. If in degree becomes 0, push it also in the neighbor. Okay. So you have a vector of in degree. You calculate the in degree of all. You make a queue. You push all in degree 0 in the queue. You keep iterating till it is 0. You take up topological sort. The front node in the topological sort order, push it. Make the in degree minus and push it and keep returning. Also pop it every time. So the queue level by level, similar to BFS, that's why Kahn's algorithm is BFS level traversing. Cycle detection using Kahn's algorithm. Okay, no node has in degree 0, algorithm cannot start. If the in degree process node size is not equal to n, that means there is a cycle. So whenever you have to do DFS topological sort, you do DFS. Kahn's algorithm is BFS. DFS uses obviously what stack. Kahn's uses Q. DFS uses inverse finishing order. Kahn's uses in degree finding. Uses recursion, it uses iterative. Cycle detection needs pathwise. Cycle detection built in. Code schedule and all of the topological sort same questions are also in degree questions, like Kahn's algorithm questions. Prerequisite dependencies, anything. In degree is the number of incoming edges. Nodes with in degree 0 can proceed immediately. Kahn's algorithm is BFS style topological of sort. And if the processed odd size is not equal to n, cycle exists. Okay, now next move on to the next algorithm, which is Dijkstra's algorithm.
Dijkstra's algorithm is your go-to method for
Hi Sunshine Didi, hello. How are you? So this is probably the most important shortest path algorithm asked in interviews. And before learning dice to understand why BFS stops working, so we've already learned that in order to find the shortest path, and if it is an equidistant graph or it is an unweighted graph, you can always use BFS because the node when encoded in a BFS is always the shortest path. But if it is a weighted graph, then you have to apply Dijkstra. So why do we need Dijkstra? We want the shortest path from 0 to 2. So 0 to 2, 5, and then these. Why BFS is because in BFS we assume that every edge has equal weight, but it is not the case for weighted graphs with non-equal weights, like with non-equidistant weighted graph. So what should you think of Dijkstra whenever you see shortest path, weighted graph, minimum effort, minimum travel time, minimum distance, minimum cost, cheapest route? You always have to apply Dijkstra. And weights are non-negative, because if weights are negative, you have to solve it with two other ways, which is Floyd-Horschel and Bellman-Ford, which we'll talk about later after this. So the core idea here is that distance node is the shortest distance found so far, and you have to keep minimizing it. Initially distance of source is 0 and all other are infinite. Pick nodes having the minimum distance. This is the entire algorithm. How do we get minimum distance nodes? With a priority queue, which is implemented as a min heap. So priority queue can be max heap or min heap. You're using min heap because you want the one with the minimum distance. Graph representation. This is an adjacency list. Relaxation concept. So this is the heart of Dijkstra. Whenever you find a path to a node from some other node which has a distance less than the distance stored already in the distance matrix of all the paths that have been encountered till now, you have to be greedy and choose this path and update the distance matrix. This is relaxation algorithm. So if the current distance to node 1 is 10, new path gives 6, you always update it, and this is called relaxation. So this is all about priority queue plus relaxation, PQ plus relaxation. So if your distance node plus weight is less than equal to distance neighbor, then always update the distance of neighbor. Memorize, this is the most important line. Why min heap? Because the distance and node you have to keep it in a min heap. So priority queue, pair of int comma int, which is the destination and the distance, vector of pair of int comma int, and greater pair of int comma int. This is how we create a min heap because the default one is max heap. PQ dot push 0 to source, which is 0 and source, which is obviously the source, and 0 the distance. The distance is minimized, okay? Complete algorithm. Distance array, source destination, make it 0. Push all the sources into the heap. Pop minimum distance node from the heap. Relax all neighbors. Push updated neighbors. Repeat. So see, we are not using a PQ because a PQ becomes a queue in case of equidistant. So you have Dijkstra algorithm. Okay. Take a distance matrix, take a PQ, take a min heap of a pair of int comma int. The first one is distance, second one is your node. Distance of source is obviously 0. Push source and 0. And while your PQ is not empty, this is the top, then pop it from the top for all the neighbors. Check the neighbor, check the weight. If there is relaxation, relax it, push it with the new distance and the new neighbor into the heap and keep on moving. You'll often see that this will continue, add immediately after popping. PQ.pop, continue. Because heap may contain old stale entries, this optimization avoids unnecessary work. E log B. The next is Bellman-Ford. Let's start with Bellman-Ford. Bellman-Ford is the algorithm to use when you have shortest path plus negative edge weights. This is the biggest difference from Dijkstra. Why do we need Bellman-Ford? Because all the edge weights are non-negative. If the negative edge exists, Dijkstra may give wrong answer. So what does Bellman-Ford solve? It solves single source shortest path, meaning source to all nodes, exactly like Dijkstra. Additional superpower, it also detects negative cycles. Dijkstra cannot do it. Interviews love this question. So intuition. Suppose this. The shortest path from 0 to 3 contains 3 edges. Observation. In a graph with V vertices, the longest possible shortest path can contain up to V minus 1 edges. Why? Because if you see V or more edges, you must repeat a vertex that creates a cycle. This observation is the foundation of Bellman-Ford. The relaxation concept, exactly the same as Dijkstra. Suppose d minus u, this is this, new path is this, then we just update it. The shortest path can have v minus 1 maximum edges. Relax all the edges v minus 1 times. Eventually, every shortest path is discovered. This is the entire algorithm. Unlike Dijkstra, we don't need adjacency list. Usually store the edges, u to v, and weight. So Bellman-Ford, what it does, you have the edge list, you have the source, you make a distance with this is int max, you make the source 0, you have to minimize it, relax it I v minus 1 times. For all the edges, take a u, take a v, take a weight. If distance of u is not int max, distance of u plus weight is less than distance of v, update it, do it v minus 1 times. This is the most important interview concept. 0 to 1 is 1, 1 to 2 is minus 2, and this 1 plus minus 2 plus minus 3 minus 3. What happens? Every time you travel around the cycle, distance becomes smaller forever. Therefore, no shortest path exists. Detection trick. After v minus 1 iterations, do one more iteration. If any distance still changes, negative cycle exists. All shortest paths should already have been found. If another relaxation is impossible, only a negative cycle can be responsible. V into E is the complexity, and of V is this. So Bellman-Ford is ideally not giving the shortest path with negative cycle. It is just helping us detect a negative, uh, a cycle in a negative edge thing, a cycle in a negative edge graph. So Bellman-Ford finds the shortest path even with negative edges. Second, detect negative cycles. Okay, let's move on to the next, which is Floyd-Warshall. Kahn's algorithm is a cycle detection algorithm, and Bellman-Ford is negative cycle detection algorithm. Please confirm. Is Can Bellman-Ford also detect positive cycles? Because it is only for DAG. Yeah, you're right. Yep, you're right. Inspiring. Thank you. Oh, today is a holiday. Today is Bakrid. Oh, no. No, today is not Bakrid. I don't know. There is something today due to which I am having an holiday. Okay, fine. So let's revise. Floyd-Warshall and then DSU, Kruskal, Prims, Bridges, Articulation Point, SCC will be left. Floyd-Warshall algorithm is one of the most important shortest path algorithms because this is same like Bellman-Ford, but the complexity is even worse because Bellman-Ford was V cross E, but it was single source distance shortest path computation, but this is multi-source single path computation. Kahn's algorithm is for topological sort. Only we detect cycle as we are not able to create a final dependency resolved answer. Yes, obviously. Kahn's algorithm is for cycle detection, but in DAG. Oh, but in directed graph, not DAG, because obviously we are detecting cycles, so it is not acyclic. But for negative cycle detection, we can use Bellman-Ford. And Floyd-Warshall is for multi-source shortest path. So what problem does Floyd-Warshall solve? Dijkstra is one source, all nodes. Example source is 0, so it will find the shortest distance to all nodes from that source. Ford also does that, but Floyd-Warshall all nodes to all paths. Yeah, so it gives a 2D matrix. What does Floyd-Warshall do? Floyd-Warshall finds the shortest distance between every pair of vertices in a graph. In the earlier one, which was Bellman-Ford, we were relaxing the vertices v minus 1 times because v minus 1 is the maximum number of edges possible in a graph of v vertices. Dijkstra, we used PQ plus edge relaxation. Kahn's was in degree. Topological sort DFS was finishing path, finishing order DFS in a stack, and cycle detection directed was with recursion stack mapping and tracking. Cycle detection undirected was with parent tracking. When should you think of Floyd-Warshall? All pair shortest path, distance between every pair, shortest path between 82 cities, small graph. Okay. When we need all pair shortest path, then obviously because it is multi-source shortest path. Core intuition, this is the most important part. Suppose you want shortest path from I to J. Should I go directly or should I pass through some intermediate nodes? Yeah, that's a core concept. So we always do via every node to get the answer. Floyd Warshall, for every pair I to J, try every node K as an intermediate node and try to get an answer. This is the heart of Floyd Warshall. Distance of I to J is from I you go to K. From I you go to K, and from K you go to J. Yes. And this is DP solution. This is top down DP or bottom up DP. This is what this is. Tabulation is, wait. Recursion is top down. Tabulation DP is bottom up. Yes, it's bottom up DP. So when we need all pair and nodes are more than 1000, else to Dijkstra for every node, which gives better runtime. Yes, because the complexity is much worse here. Meaning of formula, current short is I to J versus new route I to K to J, take minimum. Deep interpretation, this is actually dynamic programming. As shortest path also allowed intermediate vertices, adds one more possible. All nodes become available. Shortest path found, yeah. Graph representation. Unlike Dijkstra, you take a matrix of distance. Self distance is 0. Edge weights are updated. Edge exists. No edge is infinity and all of that. Floyd Warshall. For all k from 0 to n, for all I and for all j, I to k is this, k to I, and we relax. V cube is the complexity. The space is also V square. When to use which? If it is unweighted, use BFS. If it is with positive weights, use Dijkstra. If it is with negative weights, use Penman-Ford. If every pair shortest path, use Floyd Warshall. So next we are going to revise DSU. Disjoint set union or union find is the highest ROI graph topic for interviews. Many problems that look complicated become very simple once you recognize this is a connectivity problem. The DSU often becomes the best solution. DSU is a data structure that effectively answers are two nodes in the same component and merge two components. For example, 1, 2, 3, 4, 5 are all separate. Union of 1 and 2 is this. Union of 2 and 3 is this. And are 1 and 3 connected? Yes. Core operations, which is find node, which is the ultimate parent or the representative node of that component. So one is get parent and one is add. So the ultimate parent is 3. Then 1 is also 3, 2 is also 3, 3 is also 3. All belongs to the same component. Union and find. Find union. This is union find. So obviously there is find and union, two operations. Now union merges two components. Initially parent I is I, meaning every node has its own parent. Have we solved some questions? DSP. Very few questions, but yes. Where is DFS? The hell is DFS? Okay, guys. Oh, wait. Initially, parent of I is I. Every node has its own parent. Find operations. So there is union and there is find. In find, you have to get parent. So you can do it recursively. If the parent's node is equal to node, return node. So if that's the same parent. Otherwise, keep finding. Keep finding the real parent. 1, 2, 3. Find parent of 1 is going to be 3. 1's parent is 1, 2. 2's parent is 3. So the actual parent is 3. Path compression. This is the first optimization. Interviews expect this. Without compression, the finding parent of 1 will be of n, which is 1, 2, 3, 4, 5, because you have to go till 5. But after compression, all the parents are updated as 5. So while coming back, while returning from here, you also have to keep updating here. So next time your complexity will be off 1. So if it's the node return, else parent node will also get updated from find parent. Memorize this. Why important? Because this line compresses the path. Union by rank, which is the second optimization. So till now we've done union, we've done find, and we have done path compression during finding. You also have union by rank, which is the second optimization. Suppose 1, 2, this is the union or this is the union, both are valid. Idea is attach smaller tree under bigger tree, keep the tree shallow, because the height is the main problem. So attach a smaller tree under the bigger tree means approximate rank here means approximate height. So union by rank. Int parent is find parent. Int parent v is find parent. If the parents are same, then no problem. They are already in the same component. If the rank of parent is less than the rank of parent, then attach it to the smaller one, which means parent of u becomes parent of v. I have one doubt. So, why are we attaching the smaller to the larger in by rank or by size? And tell me, like, can I use the size one everywhere? Or do I specifically need to use rank somewhere? Or all the DSU problems can be solved with size? Before that, very common interview question, process edges are these, complexity is this. Elfine, which is Eckermann. The goal is to keep the track tree as shallow as possible, because every operation eventually does find parent, and find parent has to travel up the tree. Bad example. Suppose we do this, the tree becomes 1, 2, 2, 2, 2, 3, 4, 5, height is 4. Find parent you have to travel, which is expensive. Suppose we keep attaching the smaller tree under larger trees, height stays very small. Now find parent of any node is very fast. Mm. Why does union by size work? Suppose component A size is 100, B is 2. We attach 100 under 2. We make a huge deep tree, bad, instead 2 under 3 barely increases height. But like the union complexity is alpha, which is Ackermann or O of one almost, and fine parent is recursive. So is it O of one? I have one doubt. So even if we are attaching big to small or small to big, the code is going to work, right? It's just that the union complexity will be not O of one. Log n. Hmm. If only path compression, the complexity is almost log n, but with a union by rank or size, it is alpha n. Now let's move on to Kruskal's algorithm. Why Dijkstra Kruskal? I said Kruskal. So you do here, which is path compression plus union by size. Are we also updated the size somewhere? This is one of the most important graph algorithms and the most famous application of DSU, which is MST. Whenever you learn DSU, the next topic is Kruskal because DSU is the heart of Kruskal. The problem does Kruskal solve is MST, minimum spanning tree. What is minimum spanning tree? And let's understand this. We want to collect all the vertices with minimal cost. Every node should be reachable. There should be no cycle because that will add unnecessary cost. And edges exactly, which means n minus 1 edges. A spanning tree with minimum possible edge weight. So it should be connected, no cycle, n minus 1 edges. Kruskal's core idea is surprisingly simple. Sort all edges by weight. Pick the smallest edge. If it creates a cycle, ignore it. Otherwise, take it. Repeat till n minus 1 edges have been chosen. Okay. How do we check if a cycle has been made with DSU? When we consider an edge, to need to know why will adding this edge create a cycle, DSU answers this. Because if the parent is the same, that means they are in the same connected component, they will make a cycle and skip it. Else take the edge. You are also very good. I don't think so. I am just revising. I still think that I'm noob in DSU. And I don't think this. I am actually a noob. I'm still learning. I don't know. I'm quite old to learn, but I don't know. I'll just keep on learning forever. Sad. But yeah. I've seen people very good at DSA. I am very basic. Else take edge and union components. So if true, already connected, adding edge, escape, blah, blah, blah. Sort the edges, initialize DSU, process in increasing order of weights. If the edge endpoints belong to different components, take it, otherwise it cycles, skip it, union component, add weights to answer. Edge representation with an edge list. Kruskal sort the edges, weight stored first. Okay, let me see the code. This is dry run. Taking the smallest edge available step never hurts the MST. This is the key proof idea. You don't need the formal proof. E log E because of what? Sorting. Then alpha, which is Ackermann constant. This is for DSU union. So overall it is E log E only. Shortest path, minimum spanning tree. For this, source needed, no source, this, DSU minimum heap. Weighted graph. Yeah, fine. Let me see the code. Wait, we already have the code for union and union by size. You can use by rank. I use by size generally. We also have the code for find parent with path compression. So the overall complexity is alpha Ackermann. Oh, almost over 1. So you have n. You don't need a source with Kruskal. You need a source with Dijkstra. You can take 0 as a source if not mentioned. For in degree you have to take the source with topological sort. You have to take the source within degree 0, but here you don't need a source. You sort the edges obviously with you take an edge list. You initialize DSU with n vertices. What does that mean? All the parents of all the nodes from 0 to I are marked I. Sorry, 0 to n are marked I. So 1 has a parent 1, 2 has a parent 2, 3 has a parent 3. What does that mean? That every node is in a different component. So here you have initialized a DSU data structure with n vertices. This is your MST's weight till now, which you have to return. So you have to return the total edge weight of your complete MST. And you are going to iterate over all the edges because you have sorted it now. If just take it in increasing order also, once the count becomes no, you can just break, but let's see. Weight is this because it's an edge list. U and V are these. Because you have kept the weight as the first, you're able to use the normal sort function. Otherwise you would be required to create a custom comparator. If DSU's parent for U is same as V, that means they are all in the same component. So you don't need that edge because they're already in the same component and edge or a path already exists and you don't need this edge. So skip it. But if they are not equal, then add that edge to this and also union it. So because now you've added an edge, you have to union both of these. So you union by size U and V and then return the maximum weight. So this is quite easy. Okay, so the time complexity is E log E because of sorting. Next is prim. Prim is quite easy. Like this, it doesn't need DSU. So Kruskal is sort edge plus DSU. DSU is only for cycle detection. I would suggest using Kruskal in fast and interval for MST. I've seen an MST question actually. Switching. You're very good in solving and getting solution quickly. I wish I can do the same. I'm a very, very normal, average student. Anyone with hard work can do much better than me. And I know you can do much better. One of the most famous DSU union find observation. Oh, I'll do it later. Prims and Kruskal solve the same problem, which is MST. What problem does Prim solve? Given a weighted undirected graph, you have to connect all the nodes, minimum total weight, no cycle, n minus 1 edges. Prims versus Kruskal intuition. So Kruskal will sort all of them globally and then use DSU. Keep taking the smallest edges. Prim starts from one node, keeps expanding the tree using the cheapest edge, uses minimum heap similar to Dijkstra. Kruskal is edge-based MST with DSU. Prim is node-based MST with minimum heap, which is greedy. Core idea is this: we start from zero. All these are all the available edges. Take the cheapest one. Now MST is this. Now again take the cheapest one. So you just need a priority queue to pick the edges greedily. Distance node, shortest path. Okay, store all of them. Graph representation is the adjacency list. Minimum heap structure is with weight and node because weight has to be minimized. Okay, Prim's algorithm. Let's see the code. So you start from any edge, you push 0 to 0, extract the minimum edge. If it is already in the MST, node is already in the MST, then we also have to keep all the nodes that are in the MST. Add weight to answer, push one node. Okay. The code is okay here. Visited. If all of them are visited, that means your MST has been formed. Priority queue of weight and edge. Yes, sorry, weight and destination node. Now, fine. 0 to 0 is obviously 0. You just start from here. You pq.top, pq.pop. If visited, then just continue. Otherwise, market visited, MST weight added, all the neighboring. The neighbor is neighbor dot first, edge weight is neighbor dot second. If not visited, push edge weight and neighbor. And return this 1 second. You are iterating over PQ. When you get it, it is from your last vertex node. This node is not, if this node is actually neighbor. You come here. Oh, this is a node from somewhere at the end. You don't need that node because of whatever reasons. You don't need this node because there is a path somewhere at the back which is already covering it. Okay, fine. Cheapest edge crossing from MST to outside is always safe. Cheapest edge crossing from MST to outside is always safe. You don't need to prove this in interviews. Minimum cost network, connect all cities, route construction. These are all popular MST problems. What? Minimum cost network, connection to all cities. Shit, this is the lead code hard which I've seen. I'm going to solve one DSU question before moving to bridges, articulation point, and Kosaraju. One of the most famous DSU interview question is number of connected components in an undirected graph. So this is the graph. Okay. Number of connected components in an undirected graph. You already know this, right? But okay, this is quite simple to solve it with DSU. Okay. You have your edges. This is the graph, and the answer is 2, but you have to solve it with DSU. If we do union by size, every node initially belongs to its own component, so the parent is the same number, which is parent size I, size I is 1. Now when you do a union of all the edges, you start with 0, 1. Both are of size 1. Make one root parent to other. So size of 0 becomes 2. Now comes 1, 2. Root of 1 is 2. Root of this. Attach smaller tree and a larger tree, and the size becomes 3. And keep doing this. Size becomes 3. This. Let me see the whole number of provinces. This is also another famous question, which is similar question. So you have parent, you have size. You have parent, you have size. Now DSU. This is initializing it. So you make it of size n. Size also make of size n. Initialize everything with 1. You you assign the same node as its parent because they're all part of the same component. Find parent, you do path compression. If it is equal, then it's fine. But otherwise do path compression. Union by size. So you take the first parent, second parent, if they are already the same return, because you don't have to do union, they're already are in the same component, no point doing union. Attach the smaller one to the larger one, because this is for Ackerman. Uh, this is for keeping the height shallow or the tree shallow. So if this is less, then make the parent of PU as this parent and increase the size also. Otherwise, increase the size of that. Okay. Yeah. Number of provinces is a very famous DSC question. So you have done the same parent size. You've kept the parent. You've kept the size. You've done union by size. That's a constructor for your class. You have your n as a component size. You have initialized your DSU data structure. 1 second. Okay, you created a DSU object of DSU. For all the edges, you have created, this is the adjacency list. So for all, oh, this is an adjacent matrix, yeah. You have created a union of all the edges in your data structure. Then this is the number of connected components, which is called provinces here. For all the numbers, you do a parent tracking. If their parent is same as I, do provinces 1 plus plus. Otherwise, it is of some other parent. It is in some other component. Return provinces, yeah, fine. If it has the same parent, that means it is in a component. Otherwise, you have tracked and find parent. You initialize everything. You keep going till the number is the same. The number is the same initially, fine. Otherwise, keep going till the root. Keep going to the root. For going to the root, you have to go up. Yeah, you just go up. And for that number, if that number is the same, it's fine. That number is the same as that, but that number is not the same as this. Skip it, because that is a new, not a new province. Next is bridges. Bridges is an important concept. Articulation point is also an important concept, and Kosaraju is quite easy, so this is a fun concept. Why you stopped creating DSA videos? I used to watch those, very helpful. I've stopped creating DSA videos because I forgot my Apple Pencil at home. Yes, in India. I forgot my Apple Pencil in India. I have my iPad, but I don't have an Apple Pencil, so I don't create content now. But I'm planning to buy another Apple Pencil. Why don't you do pair programming? I do it in interviews. Ha ha ha. I'll do it someday. It's tough to find people for pair programming. Tarzan's algorithm. This is very, very important concept. Bridges and graph, which is Tarzan's algorithm. So we have graph representation, BFS, DFS, connected components, grid, cycle detection directed, topological sort, Kant, Dijkstra, Bellman-Ford, Flawed-Warshall, DSU, critical prims. Bridges, which is Tarzan's algorithm, articulation point, SSC, which is Kosa-Raju. So there are 18 total graph concepts. Tarzan's algorithm. This is one of the most important advanced graph concepts. Many candidates memorize the code but don't understand the intuition. If you understand the intuition, the code becomes easy. What is bridge? Bridge is an edge. If you remove that, the number of connected components increase. So bridge is an edge whose removal increases the number of connected components. Remove the edge, the graph becomes disconnected. Example without a bridge. Remove any bridge, because there is interconnectivity. A bridge is an edge whose removal disconnects the graph. Bridge and articulation points are concepts for directed or undirected graph. Bridges that classically defined only for undirected graphs. Okay. Cycle detection using parent is for undirected, with path visited is directed, topological sort is DAG, SCC is directed, bridges is undirected, articulation point is undirected, crucial is undirected, prims is undirected. Important. Very important. Kernel panic. Hello. So bridge is an edge whose removal increases. Why is it hard? Because for every edge you remove edge, run DFS, check connectivity, so the complexity is obviously going to be large. Yes. This is the brute force. This is a very nice question in which we have to backtrack and see if there is a package. And that there's a package means there is some other. We have to keep a track of shortest time and all of that. This is the most important part. Suppose this. DFS tree is this. Can node 2 reach any ancestor of node 1 without using H2 node? So this is a bridge. Yep. So we have discovery time. Key question. For every node, can a subtree reach any ancestor? Yes. Discovery time, which is Tn. Tn. What is the full form of Tn? What the time in, time out. No, not here. There's something wrong with my laptop, like it's so slow. In Tarzan, Telco, what is the Tn full form? Time in, time of insertion. Okay. Discovery time. Yeah, it is discovery time. So during this, when the node was first visited, initially DFS order, they are all like 1, 2, 3, 4. Low time is the magic array. Earliest discovery time reachable from this node or its subtree. Memorizes. Is a DFS tree after DFS if low of V is greater than, then this is a bridge. Why? Because V subtree cannot reach U or any ancestor of U. Okay, so we have taken parent, adjacency, discovery time, lowest discovery time, visited, bridges. This is DFS, so yeah, we have marked it visited. Discovery time is, so we have also taken a timer obviously. Discovery time and low time are the same initially. For all the advertises, we do it for every edge. What? For every node. Yeah. If the neighbor is parent, where is the parent? Okay. पहले टार्जन एल्गोरिथम में एक्चुअली समझ आ गया बट आई जस्ट वांट टू सी अ वीडियो डिस्कवरी टाइम वाला मेरे ये सारे मैसेज डिलीट हो जाते हैं मैसेज रिट्रेस्ड ऐसे लिखा आता है वियर्ड क्या करें ठीक है ब्रिजेस की देख लेंगे वीडियो इसकी देख लेंगे और कोसा राजू तुम जाता है ठीक है strongly connected component no I don't need this bridges and graph is SEC solved with Tarzan or Kosaraju or both? Both. Strongly connected can be solved with Kosaraju and Tarzan. ठीक है, I am not going to solve it with Tarzan. I am just going to solve bridge in a graph. See 2 videos and articulation point. Sorry. Articulation point in graph theory. Yeah, only these 2 videos. 3 years.
Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So in this video, we're going to learn about bridges in a graph. Now, what is the definition of a bridge? Very simple. Pick up any edge and if you remove it, the component gets broken into two or more components. For example, let's remove this. So the moment you remove this, previously it was connected. But can you see, this is a single standalone component and this is a single standalone component. So they got broken down into two separate components, right? Now, imagine I say, okay, if I remove this, they're being broken down into two separate components. So it's a bridge. Now, what if I say, let's remove this. If you remove this, it is not broken down into two or more components. It still stays as a single component, but that's not a bridge. Imagine I remove this. It's broken down. One here and one here. So, what is the definition of a bridge? Very simple. Any edge on whose removal the graph is broken down into two or more components. That is the definition of a bridge. Got it? Now, which algorithm will be used to find a bridge in a graph? It's very simple. We will be using some logic in the DFS algorithm. So the prerequisite is quite straightforward. You must be knowing the DFS algorithm. Just in case you do not know the DFS algorithm, I made a detailed video on this particular playlist. Scroll up, you'll find the video for DFS. Go back and watch it and come back. Okay? So the prerequisite is DFS algorithm. So we will be taking this particular graph and we know the bridges in this graph. One is this, the other one is this, and the other one is this. The problem is stated, print all the bridges. That is the problem. It states print all the bridges. That is the question. So 4 and 5 is a bridge, you can write it as 5 and 4. 5 and 6 is a bridge, again you can write it as 6 and 5. 10 and 8 is a bridge, you can write it as 8 and 10. So there are 3 bridges. I want you to print all the bridges in this particular graph. That is what the question states. To implement the algorithm to find the bridges in the graph, what we will do is we will take two separate arrays. One is the time of insertion, while the other one is the lowest time of insertion. Now what does that mean? Do you know the DFS transfer? How does DFS transfer work? Maybe it starts from 1, goes to 2, goes to 3, then goes to 4. So first operator is first time of insertion is here, second time of insertion is here, third time of insertion is here, fourth time of insertion. So while doing the DFS transfer, keep a track. When are you reaching a node? In which step are you reaching a node? So the step at which you reach the node, that is what we call as time of insertion. Got it? What is the lowest time of insertion? What it does is it finds the lowest of all. So if I'm standing here, it will look at all the adjacent nodes and take the lowest amount, but it will not consider the parent. Did not understand? No worries. I'll be doing a proper parent. You'll understand this. But remember this time, apart from parent, this is the key point over here. Okay. So let's start with the algorithm. So with the algorithm, how we start is we will write time of insertion and the lowest time. So let's start with 1. So that's where we start. So market is visited in the DFS transfer. The time of insertion is the first step, so time will be 1, and the lowest time will be 1. So the first step is the time of insertion, the second is the lowest time. Since initially you do not have any adjacent nodes, let's assume the current time is your lowest. Then we'll check around adjacent and we'll figure it out. Next, it will go to 2. So market is visited, and the time of insertion is 2 and the lowest time is 3. Next is 3, 3 by 3. Next is 4, 4 by 4. Next is 5, 5 by 5. Next is 6, 6 by 6. Please make sure your market is visited. Okay. Next is 7, 7 by 7. Next is 8, 8 by 8. Next is 9 by 9. Now here comes a critical piece that you need to understand. So at 9, when you're doing a DFS transfer of 9, it has a time of insertion as 9 and the lowest time of 9, right? Can 9 go to anywhere? If I ask you, what are the adjacent nodes of 9? It's 8, which is where it is coming in from. If you look at this, so it's a parent because 8 is following the 9. So it's a parent. And if you remember, you do not consider parent. Will 9 go to 6? In DFS, we do not visit nodes which are visit. It will not go. It will not go. But remember, of all adjacent nodes, that is what low is. But low will say, okay, I will not go there. But I'll pick up in. Your lowest is 6. I'll pick up. So I'll just pick up that and write it to myself. Oh. Now remember, this 8 called 9. So as of now, can I say 9 has no more adjacent nodes to go? It doesn't have anything to go. So it will come back. It will come back. Let's come back. So it will come back. Now when it comes back, can I say for sure that the 9's DFS transfer is complete, done in that script? It is. It is. So 9's time of insertion is 9 and the lowest time is 6. Now 8 will say, hey, you are one of my adjacent nodes. Hey 9, you are one of my adjacent nodes and you did complete your transfer. So I'll update my node. What is your node? 6. It will be. So I'll update my node to 6. So that is the definition of node. It says I will take off all adjacent nodes apart from parent. 8 did not look at its parent. It took it from its adjacent node. 6 it got, it took and updated the node. Done. Now, once you have updated, it states, hey, wait, you have done your job. Now, can 8 and 9 be a bridge? Can this be a bridge? Okay, can this be a bridge? How do I check it? How do I check it? This is where these two arrays will help. Now he says, 9 is done as the transfer. Can 8, 9 be a bridge? So he removes that. I will just remove that. 9 says, hey, you're removing. He'll ask 8, what's your time of insertion? He says, in order to reach me, it has to be the 8th step. It has to be the 8th step. 9 says, I have an adjacent guy who can reach at the 6th step. The 9 says, I have an adjacent guy who can reach at the 6th step. So even if you remove, I can still go to the 6th step. The 6th step will take me to the 7th, and 7th will take me to the 8th. I can reach you. And if I can reach you, it's not a bridge. Because the definition of a bridge is split it into 2 components. So if I'm split it into 2 components, I can't reach you back. So there's a part to reach you back. It did not get split into 2 components. It's not a bridge. So I'm sure that it is not a bridge. Now since I know 8 and 9 cannot be a bridge, so like hypothetically removed it, some hypothetically place it back. Quite nice. So 8 has done for 9, DFS is done, it has taken its lowest value, and I move ahead. Now we move to 10. So can I see it was 9 until the last step was 9 step. This will be at the 10th step, alright? Alright, 10, 10. And 10 written, and mark. It has visited. Next, 11, 11, mark it as visited. Next, 12, 12, mark it as visited. Now comes the point. Let's erase this and write the DFS of 12. So when I write DFS of 12, can it go somewhere? It says I have an adjacent node 10, but it's already visited. So I cannot go there. It's already visited. Now, if it cannot go there, because it's already visited, so you came via some path, and that is the reason it is. So this is never a bridge for sure. Because if it's visited, you have visited in the previous path. So it's definitely not a bridge. But what's our job? Low will say, wait, I know 12, it's adjacent node. Oh, I need to pick its lowest time. He just picks it and makes it 10. Nice. Next, can I say that the DFS of 11 called 12, and now 12 says, I have done it. I'm complete. So whenever it's complete, what is diagonal load is ready. I just take the loop because that's set in mind. So I take it. But once I've taken, 11 says, can this be a hypothetical edge? It's press remove it. So 11 can be reached at the 11th step. And 12 says, I have an adjacent hook hand is coming. I can survive it. You can mark everything as 0 and you'll be dividing in this. What's the this? That means they got split into two different components. They can write as IT and node. This is a bridge. You can write it as node and IT as well. Perfect. Done. What if it's visited? That means while the previous traversal was being done, previously you have visited it. So you have already visited it. So it's definitely in the same component, even if you could remove that. So bridge, not possible because you're coming by visiting it. You're coming by visiting it. So how can it be a bridge? I'll just be considered with the lowest name. So he is just bothered about himself. He'll be like, hey, I don't care. Just give me your lowest name. I'll just take it. It cannot be a bridge anymore. So it's perfect. This is how you can write. Just take the lowest name of the compare it if it can reach. And once you've done this, all the views, assuming it's a single bridges.
What the hell? What the hell? What is it?
Extremely well. So this video we'll be learning about articulation point. What do you mean by articulation point?
This is
Now,
important.
This is the given graph. Any node on this graph, on whose removed, the graph breaks into multiple components, is what you call as articulation point. Like if you see this graph, for an example, imagine I remove 0. Do you see the graph being broken into 1 and 2 components? Do you see that? You see that, right? The graph got broken into 2 components on the removal of 0. Similarly, if I try to remove 2, if I try to remove 2, did the graph return to multiple components? Yes, it did. One is here and the other one is here. The graph broke down into multiple components. Yeah, these edges will no more be there, but the graph did break into multiple components. So any node on whose removal the graph breaks down into multiple components is known as an articulation point. Now, can I say that 3 is an articulation point? No, I cannot, because even if I remove 3, the graph is still connected. I don't see any breakage apart from the removal of 3. That is why 3 is not an articulation point. For this particular graph, only 0 and 2 are articulation points. Now, in order to understand articulation point, there is a prerequisite, and the prerequisite is this particular video, bridges in a graph. The video before this, in this particular playlist, is what you should have seen. You should have understood what is time of insertion, what is the lowest time, and everything. And if you know that, then only you should watch this.
Hi Prashant, glad to see you back. Tanuja. Thank you. Unfortunately, but thank you.
Particular video which is talking about articulation point, because I'm assuming you've seen the video of bridges in a graph, because the concept that we have used in bridges in a graph is what we will be using in the articulation point. So please go back and watch it and come back and watch this video again. So if you remember the bridges video, we used 2 arrays. One is the time of insertion, while the other one was the lowest time of insertion. Now the definition still stays the same, but there's a slight tweak. Over here the time of insertion states while you enter the DFS, you store it. But the lowest time of insertion has been changed, and it states minimum of all adjacent nodes, like you take all the adjacent nodes apart from the pattern and take all their lowest time of insertions. But we also
This is bridge. What?
remove visited nodes. Do not take parent and do not take visited nodes. Why not visited nodes? I'll explain you. In the bridges video, there was nothing as visited nodes. There was simply apart from parent. Over here, it's apart from the parent and apart from the visited nodes. Why? We will be talking that in depth when I take this example. So if you did not understand the exact use of flow, do not worry. When I do a trial on this particular graph, you'll get an idea about what is the exact definition of flow here, because it's slightly different from the bridges in the graph. Okay. So in the bridges in the graph, if you remember in that video, the condition was very simple. If the low of IT, like if the low of IT in any case was greater than the time of insertion of the node, then we could say that node and IT is a bridge, right? That means if that is a node, cannot reach back to the node or before it. That means it is a bridge. This was the condition being used in the bridges in a graph of video. Now over here, we are removing an edge. No, we're removing the entire node. We're removing the entire node. So if you're saying this is an articulation point, the 5 has to reach before, not at this node, not at this node. In the previous bridges, if you could reach at 2, it was okay because the edge was removed. Over here, you have to reach before 2, somewhere before 2. That is why that slightly, we slightly change the definition of. We will say, hey, if the low of IT.
But if it was this, then it has if 5 is removed, it will not be there. Not 2. 2 can be reached from somewhere else. It has to reach somewhere.
2 it was okay because the edge was removed. Over here, you have to reach before 2, somewhere before 2. That is why that slightly, we will slightly change the definition of. We will say, hey, if the low of IT cannot reach, that means if it is greater than the time of insertion of node, that means it can either reach the node or it is greater. Even if it's reaching the node, that is of no use because I need to remove the node. So even if you reach node, that's of no use. So this is the updated condition. This is the updated condition. And there's a slight new introduction, and that states parent is not equal to -1. Yes, we have a slight new introduction. We say parent is not equal to -1. Why parent not equal to -1? Let me explain. So imagine if you have a graph like 0, and it points to 1, and then it goes to 2, and then it goes to 3, right? So apparently, if you're at 0, 0 can never be the articulation point. Why? Because even if you remove 0, it still stays as a component. It still stays as a single component. So be very careful. If it is the starting point, do not use the formula. You will go wrong. You'll go wrong. For the starting point, we'll use some different logic which I'll talk at the back end. But as of now, remember, if it is the starting point, do not use this formula because this is of no use. If you remove, it's of no use. The formula is of no use. So do not use this for starting points. For starting points, we'll use a different logic. 1 have any of its addition? No. So we will go back. When we go back, will we apply the formula to this particular guy? Because we have came back from a node. The DFS is completed. But if you remember, it's stated. It's the first guy. Parent is -1. Do not do anything for first parents. Do not do anything for first parents. Okay? Go to 2. So we'll go to 2 and we will update it like 3 by 3. Similarly, it will go here. And the moment it goes here, it will update it by 4 by 4. But here comes the twist. So it says, I've updated myself by 4 by 4. I've updated myself by 4 by 4. But I can go, but it's already visited. I can go, but it's already visited. So what I will say is, hey, listen, I will just update my loop. I'll just update my loop. But while updating my loop, I will just take this and not this. Why? I'll explain you as we go forward. We will not look at this. We will just look at the time of insertion. And that is what I'll take. I'll update it with 1. Okay. Then we come back. But when it comes back, the loop looks around it and says,
wait, we were inserting during that. What was wrong? If it was not visited, we did DFS. Else we were just updating the low. And if it is not visited, we also check for graph, which is low is minimum of this, which we also do here, which is the same. And then we check for the graph here, which is fine. But the only problem here is that we're not checking for parent. Okay. Let me see.
You're one. You're not my parent. You're not a visited node because you did your DFS. If you did your DFS, give your loop. It updates its loop to 1. Now, can I see the DFS of 2, call the DFS of 3, and I'm stuck. Now, since it is back, who will say, okay, wait, I have done a DFS. Let me see if I can be an application point. Now, what is 2? 2 is stating my time is 3. 2 is stating my time is 3. So 3 is saying my lowest is 1. So I can reach before you. Even if you're an articulation point, I can still reach. So even if you remove, I'm still somewhere in the same component. So this will not be an articulation point as of right? This is why I said greater than equal to. This is having a lowest point of 1, this is having an entry point of 3, and it can reach before 3. So this is why this is perfect. Perfect. Let's go down. So 3 is done, now we'll go to 4. It will be like, sorry, it will be like 5, 5, 5. We have 5, 5, 5. So it says I have 5, 5.
The last revision is Kusaraju. I am going to revise this again. I'm going to revise articulation point again. Articulation point, which is called cut vertex. Is that called cut edge? I don't know, I'm not sure.
No problem at all. It's a lot of information and it's
Why is it speaking? Articulation points and bridges are almost twins. If you understand bridges, this is much easier. Bridges remove edge, graph disconnects, articulation remove, yes. Exactly same. Discovery time. Earliest reachable discovery time through trees or edges of this. Is greater than equal to. After DFS returns. If low of child. ठीक है. Oh. Hmm. 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 Perform DFS. Hmm. Store nodes according to finishing time, which is topological sort. Hmm. 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 ठीक है. Shit. ठीक है. I think I'm done. Guys, I will come live again and solve all the questions of TFS now and BFS now. Okay, guys, bye.